Thank you. Thank you for inviting me. I should start by saying that given that I don't exactly know the audience, I'll try to keep it at a mix of different applications and questions for the research. So I avoid to go to much technicalities. Well, first of all, because I think for your level, it should be fairly easy to pick any paper and see the mathematics there. It's fairly elementary. So I'll go more into understanding why these models are actually useful, and what they offer. And more importantly, since we're in a university, what are the open research questions? This is more fun, I would say. I'll start by saying a bit, I'm sure all of you are working with different applications, though many of you probably working with electricity price modeling and forecasting, that stuff. I don't have an example for electricity price, but you can easily, I keep it a bit more abstract, but you can easily see how that connects in some ways. If you think about any organizational question, company, or even for a government level, you have different planning horizons. You have operational decisions, things like, for instance, I don't know, how much ice cream should I stock for tomorrow? You have tactical decisions that are longer term, and then strategic decisions. Like, for instance, do we invest in this new thing, whatever is the new thing? All these things have different horizons, and all these things have also different volume of forecasting. So operational decisions, let's say in electricity price forecasting, what would be the price on a specific hour tomorrow? You do it at the volume. You don't do it like one forecast. You may have to do, if you, for instance, we think about supply chain problems, it may easily be several millions of these forecasts. So often you end up having some kind of automated procedure, either through a statistical model or a machine learning model. But as you go more further up the planning horizon, you end up having more longer term forecasts, and typically there are one or two. And a lot of these things actually have lots more pseudo-causal models. You know, they try to say, okay, these are the main drivers. I'm saying pseudo-causal because we never really know the causality in these problems. But the idea is that now we have very few. And the challenge is that if you're trying to run, let's say, a company or a municipality or whatever, you want this forecast to be somewhat alike. You don't want the strategic forecast to be pointing to a growth in the market, but the operational forecast to be pointing to a stationary market, because eventually you will end up having waste of resources. Okay. So the question here is of aligning decisions. And you can see this kind of problems as a hierarchy. So you would have, for instance, stock keeping unit, different products and different stores for different regions, for different countries, and eventually, let's say, the total organization. That is, in some sense, splitting it now, not on the horizon, but more on the scope and the number of forecasts. But you could also think here that you would have more the operational side, and that would be typically univariate models, so building on past information. Whereas up here, you would have the more strategic side, where now you may have, for instance, judgment from experts or analyst forecasts, external. You may have macroeconomic indicators or other influencing factors. So the nature of the forecast changes across different levels. And that's also another reason why these forecasts will not agree. It's not only the scope of the modeling that makes them differ, it's also the type of information they're using that will make them differ. But at the same time, you would like to have a consensus view across the whole decision process. I'm particularly interested in the different horizon model here. That's the temporal side of the hierarchical. So if we take a very simple example, let's say we have this hierarchy. We have a few questions here. We could either model everything separately. We model, for instance, this guy here separately from this guy and from this guy, and we hope that it works. Or we can try to somehow have a multivariate model everything together. The question that we really have is that if I produce a different forecast, for instance, here I have time series A, time series B. Suppose these are two optimal forecasts. This is the sum of these two. Green line is the optimal forecast coming from this guy. The magenta line is if I sum these two things together. So you see I have a disagreement here. And that's the whole point of the reconciliation problem. If I want to express it a bit more formally, I would say the forecast of the sum and the sum of the forecast may differ. Now, if these are optimal and this is optimal, I don't really have a clear indication if the magenta or the green line is better. But I still would like these things to be aligned in the sense of not having a disagreement, because if I have a disagreement, then I have this problem with the decision making. But the decisions supported by the one level and the other level, they don't match. It could be, for instance, here, having different number of trucks to move, let's say, something in a supply chain, and not having enough people to drive the trucks, for example. So I need to have these things aligned. And that's essentially the reconciliation problem. This is what we want to have. We call these forecasts that are in disagreement incoherent, if we want to have a technical term. Now, if I do the same thinking across time horizons, for instance, here is some monthly data of people having to attend accidents and emergencies in a hospital. This is monthly data, and the same data is aggregated in different frequencies. So every 2 months, every quarter, every half year, every year. I mean, you have all background in math, so you understand that I filter frequencies, I make different components vanish, and different components become stronger and easier to estimate. So the information I would get by modeling this guy or this guy, it will be necessarily different. The time series itself has changed. But suppose, for instance, I'm trying to forecast for all the different levels a specific horizon, then I will have a different set of forecasts for that horizon. Say I'm trying to forecast a quarter ahead. Whatever will be here, here, here. Okay, here I will have to split somehow the forecast, but I will get, by the definition of having different views of the data, different forecasts. And again, then I have the question, should I model it here at the lower level, at the more disaggregate level? Should I model it at the more aggregate level? Also observe that if I would model it here, I would have to have a multi-step forecast. I will keep on accumulating error. Whereas, for instance, here it will be just one step ahead forecast. So my error will be primarily from having a misspecified model, whereas here is misspecified model plus accumulation of errors across horizons and all the covariance and all that stuff. So the question now becomes, which of these is now optimal? And as I said, you have diverse information, so the chance of getting actually different models is by definition you get different models, but also given that we don't know what's the generating process here, you get more chances of approximating a good model. So we're given this real data. We don't know what is generated from. We find the best model according to our pool of models. We make it right, we make it wrong, we make it very wrong. We try again here, we try again here. We have more chances actually to go closer to the underlying process. There is a bit of a game of probabilities here, obviously, because if our pool of model is completely relevant, this is not going to save us. Okay. In principle, what we want to do is what this slide shows. So what I have this slide, I have again accident and emergency data, weekly data now. You can see here the historical data, the same data expressed aggregate every 2 observations, every 4 observations, every 13 observations, quarter, it's weeks, half a year, or complete year. And I fit a model at its aggregation level, where here the red line is an ARIMA, identified according to some methodology. Let's call it optimal. And the red line, sorry, the blue line would be the result of a hierarchical reconciliation. What does it do? It essentially says, I'm going to combine the information from all the levels to obtain a new forecast. Let me highlight some cases here. For instance, suppose we were modeling on the original data that were given to us. Typically, I mean, if you have to solve a forecasting problem, we keep the data as they're given to us. So that's a very common case. You have your data, your sales recorded, your prices recorded on daily data, you model daily data. Is it the best approach? Typically, we don't check. So here is, for instance, the weekly data as the data recorded, and you can see the red line of the ARIMA. It doesn't do really a great job replicating what happened. For instance, there is no trend here, where clearly there is trend in the historical data. Why is that? Because, well, the variance explained by the trend is quite small, so the model doesn't care. It tries to explain the errors, the other stuff. But if I look here, for instance, by filtering all the information that exists here, it's very easy for the model to pick up both the seasonality and the trend. And you can see the blue line does the red line does a pretty decent job of replicating what we saw in the past. So already here you could say, oh, maybe I could just model this level and disaggregate. But then the question becomes, why don't model all of the levels? And if you model all the levels, whether you combine. And you can see, for instance, if I would combine information, I can reconstruct the high frequency signal here, the blue line, by borrowing information from the other levels. So that's the main logic of the algorithm we're going to see now. Essentially, it says, you're given some data. You don't know if actually the optimal level to model the data. Construct its aggregate views and model all of them independently. And then combine the information together and you're going to end up essentially with richer information in all levels. Now, in some levels, for instance, like here, with 1 to 3 data points, we don't expect the model to do much. The combined model can do something because it borrows information from the other levels. The other thing, of course, is the blue line is coherent across levels. So if I would aggregate, let's say, this blue line, I will have the blue line here. Another thing you can see that is a bit more, let's say, harder to spot is that in this level, for instance, this is half-annually data. The real model doesn't really understand that these fluctuations are not randomness, but it's actually seasonality. If I borrow the information from other levels, I can clearly see seasonality. So it's also able to reconstruct information that is not so trivial actually to extract from the time series, either because of limited sample or because of the split between signal and noise and so on. So you can see it also as a way to identify the components, not just obtain a better forecast. So essentially, that's the main idea of the algorithm. How does this work in terms of details? A very quick example, imagine some abstract hierarchy. If you want to have an example in your head, think about 4 quarters, half year, first half year, second half year, and a full year. I have the values for each of these guys. So bottom level, it's 1, 2, 3, 4 observations for a particular moment in time. And then I have the total hierarchy, where essentially is the bottom level and the other guys that are missing, the 3 guys. The reason I separate it is because I want to express the whole hierarchy for a time t from the bottom level. So I need the summation matrix that essentially maps how the information goes from the bottom level up to the top. That's a very simplistic hierarchy. You can model here whatever you want. It doesn't have to be, let's say, a simple mapping. It can be multiple mappings to reach from the bottom level to the top, depending what you're modeling. For instance, think about hierarchies that are across geographies, across product categories. They may have overlapping levels. Or even if you think temporal cases, there are more than one ways to aggregate from days into years. You can go through weeks, you can go through months, you can go through different ways to aggregate that they don't necessarily aggregate neatly between themselves. I'll show you some examples. So top level here, sum everything, middle level, as you can see there, and the bottom level is just an identity matrix. I need to have the forecast of these guys. Historical data, since I'm constructing them myself through aggregation, they will have no disagreement. But the forecasts, these are done by independent models, they will have disagreements. Even from a multivariate models, they will have disagreements. It doesn't mean that the multivariate model will be coherent. And then essentially we write some sort of a combination. Okay, so we say all the forecasts that we would have there, I need to somehow combine them together so that then they will give me the reconciled forecasts. Visually, what this formula does is very simple. I get the whole hierarchy, I forecast the whole hierarchy for the next period, then I use this matrix G to combine everything together, and essentially I squash all the information to a new bottom level, a combined new bottom level. This new bottom level then is multiplied by the map of the hierarchy, and I end up having now the full hierarchy. You may observe here already that although I get a full hierarchy, if I go back to my first slide, I may not necessarily need all the forecasts. I may, for instance, need only this forecast specifically. I gain by doing the whole hierarchy by essentially having more chances to get the modeling right. Remember the example I had with the weekly data and the hospital data. Some levels were very accurate. I will borrow that accuracy to give it to the rest of the levels. So it's not that I need the whole hierarchy all the time, but I use the whole hierarchy to improve the forecast across all nodes. Okay. The other thing you can observe here is that since I started from one time series and just aggregated, I get all this information for free, in quotes. I put in quotes because I still need to do the modeling and the computations and all that stuff. But I don't need new data. At no point did I require more additional data. So you can see that's a way to sort of help the identification of the model. The way I simplify the argument is you were given this data, nobody told you you have to model the problem on the data you were given. You may need very well to manipulate your data. And if you don't know what level to manipulate your data at, maybe do it at all the levels and combine them. So in a sense, I'm trying to minimize the modeling uncertainty here. I'm trying to take away the risk from the modeler of picking the right level or the right model. I'm saying, try many things. One of them hopefully will work. Okay. For those of you who have done GLS estimators, it's a GLS estimator, but it doesn't really matter if you remember or not how these guys work. Essentially, this Z matrix is based on the covariance matrix between the forecast errors of the independent forecasts here. Now, if you think about this, when I had the example before with the weekly data, the weekly time series was tons of observations. The annual time series was only 3 observations. That level here in the covariance matrix will correspond to the annual data. So I will have only 3 instances. Estimating a large covariance matrix from 3 instances, well, that's very optimistic. So I need to do some approximations here. One approximation is to just assume, for instance, that there are no covariances and there's additivity of the variance. So here, for instance, I assume all lower level series have the same variance. If I sum 2 of them together, I get twice the variance. If I sum all 4 of them together, I get 4 times the variance. So quarters to half year to full year. That's a very brave assumption, but I need to estimate now. Okay, so I'm putting a very strong assumption, but I minimize estimation errors. I can relax it a bit. I still have 0 covariances, but now I estimate the variance at its level. And here I could group it. I could say, look, all the bottom level series is the same series, it's different quarters of the same series. I could just assume all the sigmas here to be the same. Or I could say, no, the sigma changes across the period of the year. You pick how hard you want to make your problem. Or I could go one step further and estimate everything. Of course, with 3 observations, I don't want to estimate the whole thing, so I'll use something as estimator. But these have been well researched in the literature. The point I'm trying to make here is that we're not actually ever recovering the true structure. We're doing an approximation because the real problem is much larger than what we want to tackle. Okay, and I'll show you some additional results on this as we proceed, because there is actually a lot of arguments to prefer rough approximations rather than the very elegant approximations. Depends what's your objective here. We will reach there. So the idea is, you saw the maths are very easy. I have a set of matrices, I solve the GLS, I plug in some approximation for the covariance, and that's it. The rest is based on the independent forecasts. An observation we can make here is that if I was trying to model the same thing as a multivariate system, this can easily explode. I have here a very small hierarchy. Already that is quite tough to model as a multivariate model. You will tell me, no, it's very easy to put a multivariate model there, depending on the complexity of the multivariate model. If I have to model univariate stuff, it's always much easier to do. Okay, so it also gives me more flexibility in terms of how I'm modeling things. Right, you can see it as a way to combine forecasts. I mean, I saw it's a combination of forecasts essentially. And through that, you hope to improve accuracy. There is plenty of evidence in the literature that forecast combination helps with improving accuracy. I don't have the results here on the slides, but effectively what happens really is that if you think how the variance and the bias of the forecasts works through the hierarchy, you kind of guarantee that the combination will be favorable. You kind of guarantee the negative covariance and all that stuff to occur, which is a very neat property, because in forecast combination, the biggest problem is what do I combine to obtain the negative covariance to have the improvement in accuracy. Through temporal hierarchies, we can show that actually the chance of getting an improvement is pretty high. So that you stack essentially the cards in your favor by doing that stuff. And you don't really have to worry so much about what you're combining. And the other thing here is that you can have a diversity of models. So if I would try to model this as a multivariate problem, having, for instance, here models for, let's say, intermittent demand, plenty of zeros and some observations. And here, for instance, having some continuous model, let's say an ARIMA or exponential smoothing or some neural network. And here having some macroeconomic model. Putting that in a multivariate model, that would be an extreme headache. But now I can do that. I can have diverse set of models and diverse set of information. And through the reconciliation, I also do the contemporaneous connection between the models. So it gives me a lot more flexibility in how I approach the problem. It allows me to make better use of available information. Also consider here that the variables, if I'm looking at the temporal side, for instance, here will be annual variables. I can find macroeconomic variables that are annual, but I cannot find macroeconomic variables that are, let's say, daily. So it allows me actually to provide the daily data, information that is sampled at an annual level without having too much fuss on how to model it. I don't need to think about now casting or different ways to expand or interpolate my data. I let the thing do it by itself. Okay. So for instance, here, if I have external information and here I have very high frequency data, I do the reconciliation and then the information is incorporated down there. Here's some evidence from the literature on papers, at least I've been involved one way or another, of improvements in accuracy, different metrics and horizons and so on. I'll pick up on the last paper here, because the interesting thing about this paper is that we also try foundation models. I don't know if you're familiar with foundation models. Essentially, since we saw that the large neural networks or transformers work for other problems, we said, let's not think about it too much. Let's try it on time series. Why I find that interesting? Suppose, for instance, this paper, we use ARIMA or ETS or something like that. The way that TIFF works through the model combination, you can show that the more misspecified these models are, the larger the gains you get from TIFF. But in those simple models, you can kind of find what is the misspecification, you can do a simulation, and you can see exactly what components you're missing. With foundation models, that's a bit more complicated because, well, first, we typically do not know what they were trained on. And secondly, even if we knew what they were trained on, I don't think we can confidently say we understand how they work or exactly what components they have modeled. So they have a different nature of specification. And what I found interesting, at least in that result there, is that as long as there is some specification in the model, which for real data will be almost guaranteed, you expect to find a gain in accuracy, no matter the modeling family you're going with. So you can see that's a way to robustify your forecasts in some sense. And we have some more published results, but the gains you can see, they're always, let's say, 5 to 10% across papers, which I would say for forecasting, if I don't even care what is the base forecasting method, that's pretty helpful. You know, you give me your favorite method, I plug it in through that, we gain the accuracy benefit. Yeah, so that's the thing. Of course, since you're aggregating data, you're biasing your performance more to the longer horizons. It doesn't mean you don't gain in the short horizons, but you expect bigger gains on the longer horizons. Yeah. So here's, for instance, some example of intermittent data, just to give an illusion why this thing works well. So intermittent data often happening in expensive products or spare parts, but you can also see it in high frequency sampling of, let's say, demand data. What you have plenty of zeros. You don't know when the zeros are happening, and when it's non-zero, you have also an unknown size of the demand. So here, for instance, two examples. These are coming from spare parts for automotive, I think. Typical way we model that is the things like Croston method and so on, which essentially what they try to do, they try to find the average inter-demand period and the average demand size, and then they give you a ratio between these two, which is the red line here. Obviously, this is not very important. You can, of course, put probabilistic forecast around it, that's fine, but like, you don't really extract much information from the time series. This is for that specific data set. I'm actually wrong. This is not an automotive data set, it's spare parts of aviation, yes. Percentage of zeros in the time series, you can see many time series has tons of zeros, and this is the variation of the demand. If I aggregate the data, obviously I will reduce the zeros. If I have 3 periods and none of them is non-zero, the aggregated is also non-zero, okay? That doesn't tell us so much, but this tells us much more. This time series aggregated becomes this time series. This is pretty easy to forecast. It's just an up and down thing. This time series aggregated becomes a very easy series to forecast. So you can see actually how through the aggregation, you can actually obtain structures that are much, much easier for the modeling to happen. We don't know how to do that stuff down here. But if I reconcile now this and this, I will obtain the seasonality here. Remember, again, the example I had before from the accidents and emergencies, where I could obtain the seasonality on the high frequency data by leveraging the low frequency data. Same here. I take the information over here, plugging it here, and now the uncertainty of zeros is not so much of a problem. Right. Another, for instance, case would be when you have, let's say, technology, mobile phones, computers, and so on. Now they have short life cycles. If you think about the supply chain of these problems, effectively, you don't have the opportunity to fix your production. You get the production forecast and you hope it's right. And then it's more a matter of distribution of that product globally. You don't have essentially the capacity to start refining your production because you're already starting to produce the next product. So you want to have at the beginning of the whole process, this is the whole demand life cycle of the product. I think this is a laptop and it lasts about 1.5 years, if I'm not mistaken. About here, you want to have a fairly accurate production forecast. And once you have a forecast, then you have the operational forecasts, a shorter term horizons. What's the problem here? The problem is that life cycles follow what we call the diffusion process, this curve. So essentially the growth of the market, plateau, and then essentially replacement from the next generation or people lose interest. And the operational forecast is shorter, so you don't see the whole diffusion. But let's say if you would model an operation here by univariate forecast, you could say, oh, look, there is a stochastic trend, but not really. There is a diffusion. You see where I'm getting at here? If I would look for the whole life cycle, the trend is a process that is well known. If I would model it for shorter horizons with the classic time series toolbox, I would say, oh yeah, there is a non-stationary time series here with a stochastic trend. But it's not exactly that. I know the trend is a different process. Instead of having to now come up with a new model that could do short-term or high-frequency forecast with diffusion curves and all that stuff and hoping to estimate it, I can just model that separate temporal levels. So I can take that dynamic that doesn't exist in my typical univariate models and embed it in the univariate models. So I'll give you directly the results in terms of this is, for instance, this is data from clothing manufacturer. So fast fashion, they produce all the products here. They haven't yet put colors, let's say, on the t-shirts, but they need to get all the production going here. At some point, they start saying that many will be yellow, that many will be red, blue, put some stamp there and so on. And that's the demand once it goes in the market. You can see again, you have the diffusion curve and you have all the short-term forecasts. Combining the two, you get essentially the short-term forecast that can understand the life cycle. So that's on real data, on more high frequency, the other one was real data on lower frequency, laptop, as I said before. And here's kind of what happens with the accuracy. Mean rank, so I go non-parametric. So between three models, which one is the best across times? This is the horizon you have. Sorry, this is estimation sample, not the horizon. So how much data you have observed? I've observed only this, I've observed from here to here, and so on. When you have limited data, the simple univariate models win because they haven't seen the life cycle yet, essentially here at the very beginning. The life cycle models don't have enough data to estimate, but once you've seen the whole life cycle, then they are better than the time series models. The hierarchical model stays more or less flat performance in the middle all the time. It's not that it's going to always be better, but it allows you to combine the two views without having to fuss with new models and new approaches and solving your estimation issues and so on. Obviously, I can enrich further with additional models, let's say with economic conditions and whatnot. And here you can see the weekly data aggregation to yearly data, where you can see that the hierarchy can have multiple mappings. So you can have from weekly to bi-weekly or weekly aggregating, but from weekly to quarterly, you cannot aggregate neatly from everything. So that S matrix I had before, the map can be as complex as you want it. This is just a visualization. Now, I started the whole thing by saying you can have hierarchies across different sections too, but we focus more on the cross time. Obviously, you can combine the two problems. If we want to make this problem realistic, the cross-temporal is the only problem that exists. The other problems are a bit academic. Let me explain why. Suppose I'm modeling, again, the most interesting product, ice creams. I will have here essentially ice cream of a particular flavor, another package size, whatever I'm doing there. I don't care about, let's say, vanilla ice cream. I care about vanilla ice cream for next week to support the supply chain in terms of inventory. I don't care vanilla ice cream at the total company level for budgeting. I care ice cream there. I can also do the same kind of analogy here on the temporal side. A particular product is useful maybe for a short horizon a particular product for multiple years ahead is not interested. For multiple years ahead, I'm just going to go to the next slide, I care about long term on the aggregate, short term on the disaggregate. So you can slice it diagonal, if you wish, between the cross-temporal problem. If I want to map real decisions on this hierarchy, I don't actually need all the nodes. But we keep all the nodes because they give me this richness of the forecast combination. The point I'm trying to make here is that you will see a lot of the literature dealing with the one side of the problem or the other side of the problem. There are very few real problems that actually you need only one or the other side. The cross-temporal problem is actually the full specification. And here what we have is the relative effect of the different sides of the hierarchical. So up here we have three different types of reconciling the temporal side. No reconciliation, two different approximations for the covariance matrix. I have that slide with the covariance matrices. And down here are different options for the cross-sectional. So none for none, and again, different approaches for the covariance matrix. What I want you to observe here is that the biggest drop in the error happens when I shift from no temporal to some temporal. Whereas when I'm moving from just the cross-sectional, there is some improvement in accuracy depending on your covariance estimator, but it's not so large. And there is a good theoretical reason for that. If I'm going to gain anything from the forecast combination, I need the covariance of the forecast errors to be favorable. When I have cross-sectional data, I cannot guarantee that. You may have products in the hierarchy that are completely irrelevant. Think again about a big, let's say, manufacturer. You go to the supermarket. You may buy pasta, you may buy coffee, you may buy ice cream. Are these things correlated? Maybe yes, maybe no. I don't know. And that's the whole point. But when I look at the temporal side, I guarantee the correlation to be favorable. That's why the temporal side always gives me a better accuracy improvement. In fact, for the cross-sectional, we cannot guarantee accuracy improvement. For the temporal, we can kind of guarantee it. So the two sides of the problem are there. But remember, for decision-making, it's not only the accuracy that matters, it's also the coherency. I want to be able to claim that their forecasts align so I can take a unified decision. Again, I have the example, for instance, with ice cream, pasta, and whatever I use, that's not coffee. I may not care necessarily about the products themselves in agreement, but I need to load all of them up in a truck to send them to the supermarket. That forecasts have to be reconciled with the individual sales forecasts. So I still need the coherency of the forecast. It's not only about the accuracy here. A bit abstract. How does the cross-sectional work, cross-temporal work? Well, essentially, you do two reconciliations at the same time. You have, let's say, the whole hierarchy on the quarterly data, on the semi-annual, on the annual data. You would have three different reconciliations, which you could put together. That's a very simplistic view. You can, of course, solve it in one simultaneous way. You don't have to split it like that. But the reason I'm presenting it like that is because it allows us to observe something. If these, in principle, are trying to reconcile the same stuff, but they will not be identical, it means that here, I have some estimation error. That estimation error is not coming only from the data, it's coming from the misspecification of the hierarchical problem itself. So let me take that one step further. Essentially, when you think about any forecasting problem that you can save into hierarchy, the first step you have is that you have some modeling do per time series. That will have some uncertainty. There is no way to believe that whatever model you did is correct. Either estimation errors, either model family errors, or whatever you want to call them. There is always some uncertainty there. Based on that uncertainty, I will obtain the forecast errors, which I would plug in my covariance matrix. So these errors will be uncertain as well. Now, so this guy here. I will have to select different approximations for the covariance matrix. This guy will also introduce some uncertainty. Maybe one approximation is harder than another one, so we'll have an estimation uncertainty, but also have the uncertainty of picking the wrong estimation, the wrong approximation for the variance. So all I'm trying to say here is that you have confounding uncertainties through the chain. You have the basic one that you cannot avoid anyways, the modeling, and the moment you go hierarchical, it's not like the hierarchical machinery is somehow deterministic. You obtain a lot of uncertainties there. Some uncertainties are compounded from the residuals, some are coming from your modeling choices. And that will eventually give you the final forecast. Where I'm getting with that? Here is different ways to approximate the covariance matrix. Again, simplistic views. For example, here I have same style, 4 quarters, 2 semi-annual, 1 annual. To simplify the thing, I could just say all of them have the same variance. This is a bit idiotic. There is no way the annual would have the same variance as the every quarter. Or I could do what I did before, the structural case. Or I could say, well, look, I can estimate these guys and I can analytically then construct these guys. Or I can estimate the whole thing. Or I can do block diagonals and so on. Different ways to do it. What I'm having here as essentially as a different thing is how many stuff I estimate. And here is the accuracy results across multiple runs for different sample sizes. So here are the different sample sizes. Here are the different estimators from simplest to most complex. Well, empirical is not the most complex. Let's say these guys are the most complex. Empirical is just the empirical. What I want to observe is that the location of these distributions, as shown by the median, can go lower as you increase the complexity of your estimator. But the variance of your performance can also go quite wide. So now you have to balance two things. You have to balance your accuracy against your reliability. As you let the system run across periods, is it reliable or it's going to end up having some explosions? So, and that's a sign we don't often care so much about the forecasting because we often see the forecasting problem, at least in academia, as a snapshot. Here's my data set, here's my test set. I do my rolling origin or whatever evaluation as complex as I want, but that's it. I'm not actually collecting more data, rerun, and so on. So we don't really observe the quality of our performance across time. If you wish, this would be not the distributions of the root mean squared error across time, it would be the distributions of the errors that would be aggregated in the root mean squared error. So there is a question of reliability here, and the argument we're making here is pretty straightforward. Essentially, that when you choose how to reconcile your hierarchy, it's not only a question of obtaining the best accuracy, but it's a question of that accuracy being consistent over time. And we don't know how to solve that problem yet. So there is a bit of an open question there. I mean, we don't know how to solve that problem. You know, let's say that this is supposed to be one of the best approaches in the literature. It doesn't map to something that's consistent all the time. And that's a bit of the problem. I mentioned at the very beginning that very simplistic approaches, like this guy, that you estimate nothing and you plug in the numbers, they seem to work well. And you can see, for instance, here is this solution here. In some cases, it explodes. In some cases, it doesn't explode. But the difference from this guy, actually, statistically speaking, they're not that massive. And that's a small hierarchy. If I would have a large hierarchy, then the performance of this guy becomes even more relevant. You know, think of risks about going for electricity price forecasting, like, for instance, the paper I mentioned before with the foundation models. If you go from daily data up to annual data, that is a substantially larger covariance matrix. So substantially more stuff to estimate here. And so you get it. Okay. I mentioned about mixing different nature of information. Here, for instance, is the case where we're using leading indicators. So what we have here, this is based on data from a company that produces, that supports automotive. So they don't produce final product for automotive, they're in the supply chain of building cars, trucks, and so on. This is their sales. This is a leading indicator, so a variable that you can signal kind of your sales from past months. So you can see they co-move, there is a correlation between them. And I could tell already, let's say, almost 1 year before, by following the red line, what will be the sales of the company. Okay, that's a leading indicator. It's very easy to show that with macroeconomic data. So, for instance, you could have, in this particular case, they're manufacturing. These are their different products produced in different plants across Europe and USA, I think. I don't remember well. At the total level, we're trying to obtain this macroeconomic indicator. So, for instance, how will the economy move, will affect their sales, and so on. Again, I had the example a bit before as well. Modeling this macroeconomic information up here is fairly easy because, well, I have the data. And secondly, by aggregating all these guys up, a lot of the noisy part of the time series gets cancelled out. Whereas modeling the macroeconomic information down here is pretty hard. So I can use the hierarchical construct in some sense to have here a complex econometric model, have here a simple univariate model, let the hierarchy do the discussion between the models. And what I show you here essentially is the results not in accuracy, but in inventory performance. I don't know how many of you have done any inventory simulations, but the way to look at it is typically we say how much stock was left in your warehouse, because that's essentially money that was not sold, and how much you did not sell. Fill rate is the percentage of demand that was satisfied, simplistically speaking. Here is the 1 minus that. So the best solution is to the origin of the axis, okay? And effectively you have here for different target fill rates, you simulate. What you want to see, you want to find the curve that dominates. So the green line here and the magenta line, there are models that are using this hierarchical construct to have on the top level macroeconomic information and give that to the level we're doing actually the inventory decisions. If we would just use univariate models in the inventory decision level, so this is just the univariate model in the inventory decision of the disaggregate data, and it underperforms. And this is we would try to use macroeconomic indicators at the decision level again, and also doesn't work. So you simplify a lot your modeling, and you allow this borrowing of information across levels. And obviously, you can see what the variable is more relevant for your decisions. So essentially, you do all the modeling at the top level, and you just carry that down. How much do you carry that down? It goes in the covariance matrix. Okay. Again, think about the context of forecasting. We don't forecast for the forecasting itself. We forecast to support operations and decisions. So think, for instance, about a company that has multiple decisions that will take. For instance, we have the staffing, and you produce a forecast, probabilistic or not. You would optimize that, and then you would say, all right, this is the scheduling for how different people would work. Then you would say, suppose this is a transportation problem, you would have your network, and you would say, all right, I need to forecast the demand at each node of the network, probabilistic or not. And then you would optimize it and say, this is how I would route my trucks. If I have the routing working, but not enough drivers, well, it's a problem. If I have too many drivers, I have additional costs for no reason. I can make the same argument for the trucks, obviously. So here we have two different decisions running in parallel. And this is where it gets a bit interesting, because I need to have essentially sufficient resources to run everything jointly. But as forecasting problems, these are living at different levels. As optimization problems, these are also living at different levels. One would tell me, why don't you make a joint peak optimization problem? I would say, good luck. It becomes quite messy. That's the reason why. But let's forget the optimization side. Even the forecasting side, it's itself quite messy to do this multivariate, because you have different types of information and models that go into doing the two different parts. And the three cases we did discuss. We want coherence, so we don't have waste or not enough resources. So the whole point here is of this cross-temporal modeling is that itself is very easy to do. You can decompose your problem into your different parts. You can forecast it separately. So for instance, you could have them doing it, every department doing its own stuff. If you leave it as such, they will not agree in the direction of the future. Through the reconciliation, you can make them agree. That's pretty trivial. But here's where it gets quite interesting. You are all working at the university or studying at the university. And at least for the academic colleagues, you may have tried to do research with other departments. And you have probably faced the problems of every department doing its own stuff, having its own objectives. Students may study, courses borrowed from other departments. Good luck making timetables work and all that stuff. Why? Because humans are a bit difficult. Numbers are easier than humans. And humans don't really like to talk to each other. I mean, they like, but they don't like to, when they have an objective, they want to keep it tight. What are we doing here? We make the forecast align without having the two humans talk to each other. You still work with your maintenance colleagues. You still work with your routing colleagues. You don't have these people to talk to these people. The mathematics does the reconciliation. So effectively keep on working on your own world. I mean, by all means, talk to your colleagues. That's all right. I'm not going to say no. But you don't have to obtain reconciled decisions. And this is actually the biggest advantage of this way of thinking, that you can allow to overcome information silos. Here I'm giving a very simplistic view of an organization, but you can think of any type of information silos by having essentially the reconciliation done as a post-processing step. And then you can return this post-process step back to the teams and say, okay, that's now a coherent common view of the future. Let's work on that. They don't have to have the same unit or scale of modeling. That's why we need the cross-temporal hierarchies. This may be long-term, this may be short-term. It doesn't matter. The information can be done coherently as we saw before. So that's, I would say, is the biggest advantage of the whole thing. So this so-called one-number forecast. Forecasts are still done locally. We don't have to append the whole organizational structure. They do the best they have with the information they have, the expertise they have. Consider also that in practice, a lot of the forecasting requires judgmental or contextual information. If you have an expert doing a forecast for, I don't know, 10 years, it's not just a forecasting model that's good, it's also all the knowledge that this person has. Knows, for instance, that the suppliers do this funny thing every February. You know, all this information that is not captured in the model or in the database. And the information sharing happens essentially this, I would say, analytics way, rather than having actually to make this. Now, you know, this is all fine and nice. The empirical evidence is still lacking. It's work in progress because it's quite difficult to have people contribute to research from different departments. It's not only having them talking to each other difficult. So this is a big work in progress to demonstrate the empirical evidence on that. But at least from a modeling, from a framing point of view, it's pretty straightforward. The other thing that is quite interesting here is that you don't need to have this as a centralized decision. The hierarchy doesn't have to be complete for it to work. So for example, you could say, I deal with this as step one, step two, these guys, and you just expand your S matrix. It's just linear algebra. There's nothing special there. The forecasts are done independently and locally. You don't have to have the whole problem to start solving it. You can solve piecewise whatever you need. Okay, but there are still a lot of information, a lot of questions coming from the point of view of how humans accept this or not accept it. Like, you give me your forecast, it's 100. Then I come back and tell you, by combining all the organizational information, your forecast is not 100, it's 97. You may insist, no, it's 100. How do you deal with that? You know, stubbornness. It's a big problem. But you get it. Okay. I can see these cross-temporal hierarchies as a statistical device to improve accuracy because of the forecast combination, because of combining models of different families and information in each model that may be diverse. But in practice, so here I have, for instance, geographies, product stores and so on. Here I have temporal. Decisions are not taken in all combinations, are taken only in a few combinations. This opens up a different question, which is the question of how do I evaluate if a solution now is better than before? If I would have a single time series, easy. Measure your bias, your accuracy, whatever is your metric. But if I have now multiple time series, how do I do now about the combination? No one would say, there is no problem. Just take a scale-independent error. Well, yeah, but the decisions supported by these guys are very different. If this is, for instance, the budgeting decision and there's not enough money to run the routing problem, I don't care if you're accurate here, you don't have enough money to run it. So there is a weighting there happening. What I'm trying to say here is that if I would try to find now a way to either optimize my modeling selections, think about this reliability versus accuracy I presented in the previous slide, or I want to just say an argument of maximum accuracy, the score I'm going to use to obtain that is not straightforward. It becomes a multi-objective optimization, essentially. And if I would have a multi-objective and I want to linearize it to make it simple, I need weights there. I don't know how many of you read multi-objective optimization literature, but it's fantastic literature because often it results in the conclusion saying, and the experts will give us the weights. Not in all cases, okay? I'm exaggerating a bit here, but that's very tall order. Practitioners do not know how to do multi-objective optimization, right? So that remains a bit of a problem. It's easy for me to say, oh, it's a statistical device, it will improve your accuracy throughout. But if I want to go for the really optimal decision, I need to translate this problem into multi-objective. And here's an example, for instance. I just have two levels, weekly target for weekly target. Accuracy of different models. So the more on this side, the better accuracy. The more on this side, the better accuracy. I don't have a globally dominant solution. I don't have a solution that gives me the best performance across both dimensions. I have locally dominant solutions and some solutions that are always dominated by the others. But saying which is the best solution really depends how I weight my two objectives. So that's a bit of an open question. How do we actually, can we somehow automate that? Obviously, in practice, what we will do, we will sit down with the people who take this decision and this decision, and we will come up with some compromise. But more interestingly, for the modeling point of view, because we have this hierarchical structure, is there a way to obtain from the hierarchical structure the weights? That, to me, remains an open question. Yes, the other problem that we have kind of missed in doing all that is that most of the time, as thought, you work very well as a snapshot. If you keep on running it in time, you have another problem. Let me show you what's the problem here. Suppose I'm having my data on Friday, I'm doing all my forecasting, and I'm doing here, let's say, simply a temporal hierarchy, and I have two levels of modeling. I have at the daily level a forecast, and I have at the weekly level a forecast. One decision here, one decision here. I have one more data point, one more day. I will rerun my forecast here. I don't need to rerun my forecast here. I have it already. But this forecast, so here I would reconcile all the forecast, everything would agree nicely. This forecast is conditioned on different number of data points. There is no way this guy would agree with any of these guys because it has more data. There's no way. You may be lucky, but you get the point. Okay. And as I keep on doing now this across the whole week, these 5 daily forecasts cannot be reconciled with this guy here because when I produce this weekly forecast, I just didn't have this guys. I just have a static snapshot here. So what we have here, we have an incoherency in the vintages of the data. I have multiple vintages, and now the coherency is not on its hierarchy is reconciled, that's fine, but across the vintages that take the decisions, they're not. And the problem here is that in order to reconcile everything, we need to somehow have information from the future. Reconciling that forecast down here is useless. I need to use that forecast up here. Reconciling that forecast with these guys works for the first day, but these days I cannot reconcile. So here we have another problem that if we run this temporal modeling across time, as we update the information in the high frequency, we will have an incoherency that we don't know how to resolve. Okay, so does this now break the whole deal? No, it doesn't break the deal, but it's not optimal. So here is, for instance, a problem with check staff scheduling. Think about the call center. You will have an understaffing cost. You will have an overstaffing cost. You have a cost to get people last minute, or you will have a cost to tell people, well, thank you for coming. You can go home now. You can translate this cost as you want. Okay, essentially, you can create scenarios by changing the weights of each different cost. And we make some different scenarios. It doesn't matter actually what scenario is exactly the point. A pseudo-deterministic case, a use vendor case in how we optimize this guy. You can see always that if we do reconciliation, the blue thinks this is cost. Okay, both times cost. The reconciliation, even if it's suboptimal, even if it is built as incoherent, it still provides value when we look at the output of the optimization. And if we do it proper optimization, so we don't assume either deterministic or use vendor, we go for a full mixed integer linear program, we can again see that the reconciliation still helps. When we do the probabilistic modeling, we still have the reconciliation helping. So even if we don't resolve the vintage problem of the coherency, we still gain value, but it's clear there is a theoretical mismatch there. There is still something we cannot, at least I haven't figured out a way to solve it. So that's an open question, and if the whole argument is make things reconcile so we can have an aligned decision, the previous slide kind of explains that, yeah, that's still not achieved actually. It's achieved in snapshots, not in the rolling case. Another thing that is quite interesting, especially now with machine learning being almost everywhere, is that we can have machine learning models running decisions at a very high frequency, second by second, minute by minute. But they can also go wrong. So it's useful to have human supervision. We cannot expect a human to supervise a model at that frequency. What we can do, we can have the human running at a different frequency, the machine learning model running at a much higher frequency, and effectively, if you look at it like that, it's a reconciliation problem. I would have the human reconciling the decisions, in some sense, controlling or supervising the machine learning. The difference here is that now our reconciliation is not the optimal reconciliation before, but it has to be biased towards the human, the supervisor. Okay, so that's one way you can frame essentially. You may have read in the news, for instance, in a high frequency trading. Algorithms can go wide. That would be one way to control. But it's not only for these extreme cases. In general, we want to be able to have some trustworthiness in the forecasting system. And if it becomes a high frequency black box, trustworthiness goes a bit down. Okay. Yeah. So let me conclude. Temporal hierarchies, I mean, they've been out now for about almost 10 years. So I would say it's a newish approach. It's fairly easy to show that your performance in terms of accuracy will be at least as good as your base forecasts. The evidence in the literature that you will gain a benefit in accuracy is a bit overwhelming, but there is also good theory to suggest that this is the case. It's not just the empirical evidence. Out of context, that is, you give me data and I do forecasting, you will gain accuracy. Within context, you also get the coherency. You get this alignment of decisions. It's, for academics, that's sufficient. For practice, this is the real value. You have some benefits in terms of, for instance, avoiding to see how to make people work together. You can let the math do that stuff. But obviously, there are some questions like how much acceptability will be that in practice and so on. And there are still quite a few open questions like the evidence coherency. I had it in the last slides. We need to figure out a way how to formulate it so we can optimize it. I mean, you can write it down quite easily, but you use information from the future. Conditioning everything on the same time period, I have not seen someone managing to do that. And of course, there are, if we go in the technical part, which I skip completely here, there are a lot of things to say about variable selection across a hierarchy, more estimation programs, comparison with multivariate. Should I have fully independent models, or should I hold chunks of the hierarchy as a big model and then reconcile across levels? Tons of technical questions. Some are interesting, some not so interesting. But overall, very easy to implement. You saw the maths was just one slide with the minimal equations, very short equations. So it's very easy to use, very easy to implement. You don't need tons of new data because you just have the high frequency data and you aggregate them internally. It's quite trivial to do. And to run it, there are plenty of packages. I don't actually write here the packages, but there is a nice package by a team in Italy called Foreco that does many different variants if you're going to do it, and it exists both R and Python. Yeah, here are some references. I picked the references essentially to give you a bit of a view of different things that happen. So that's the paper that started the whole discussion. This is a bit simplistic compared to what I presented here in terms of temporal hierarchies. The problem is that we haven't managed to outperform it. So somehow it's still better. We have some theory why it's better, but it shows that the formulation we have right now is not the best. This is showing a bit on multivariate models, some properties that it's helpful to estimate the things even in the lower frequencies, even though you cannot really, like forcing the multivariate aspect in all levels. Essentially, this is the main paper on the theory of the temporal hierarchies. Here we introduced the cross-temporal side and we saw how that works. This is on showing that you can extract structures from data that are 0, 1. I had the slide there. This is about the stochastic element of the reconciliation, essentially the reliability versus accuracy. I think that's still an open question. This is about the multi-objective part of the problem, which is still an open question. And this is giving you a bit more the organizational side of things. But I mean, obviously, You can see I'm covering all of this. There are many other people who work on the area, especially there's been a lot of very interesting work on the estimator side. If we can take, for instance, advantage of autocorrelations in the estimation, or using, let's say, pruning techniques, either statistical testing or information criteria, to eliminate components of the covariance matrix so that we make it more stable, and so on and so on. So it's a good active area. At least in the conferences, we can still fill up the rooms. So it seems to be working well for us. I'll finish up here. Questions?